In order to confirm de Broglie's hypothesis, we must show that particles can exhibit wave behavior. In 1927, the first confirmation came when American physicists Clinton Davisson and Lester Germer successfully produced the diffraction pattern of electrons scattered from a single crystal of nickel. For one set of data, they used a beam of electrons accelerated with 54 volts. See if you can find the wavelengths of those electrons. In this problem, at first we have a voltage that is used to accelerate a charge. If we use a voltage to accelerate a charge, we can use the conservation of energy. The kinetic energy gain comes from the potential energy loss. The kinetic energy gain in this case is 1/2 mv squared, and U equals to QV. So the charge is 1E and the voltage is 54 volts, which means these electrons will have kinetic energy that equals to 54 EVs. Although we don't need that now. Right now what we need is the speed, so that we can use the speed to find the momentum, and then we can use the momentum to find the wavelengths. So let me solve for the speed first. If I solve for the speed, I can multiply by 2 on both sides, divide by m, and then take square root. So this is twice the QV over m, and then the square root of it. So the wavelength of this electron would be h over momentum, which is h over mv, and this will be h divided by m times this thing here, square root of 2qv over m. So this will be h divided by square root. If I can simplify this part, I get 2mqv. Now I can plug in the numbers. Since everything I'm plugging in will be in standard unit, I'm going to use h, that is 6.63 times 10 to the negative 34th, the joule second Planck constant. And then down here I would have square root of 2 times the mass, 9.11 times 10 to the negative 31st, times charge. For an electron, the charge is 1.6 times 10 to the negative 19th coulomb, and then the voltage is 54 volts. So if I do this, I will find the wavelength to be 1.67 times 10 to the negative 10th meter. 10 to the negative 10th of a meter is also called angstrom, and we write capital letter A with a little circle on the top for angstrom. An angstrom is about the size of an atom. So the wavelength of these 54 eV electrons is 1.67 angstroms. Remember that we need a slit distance similar to the wavelength to produce a significant diffraction pattern. With this wavelength, we can use atoms as slits. In a nickel single crystal, the atoms are arranged in the same repeating manner. Because the distance between atoms is similar to the wavelength of these electrons, Davisson and Germer were able to measure the diffraction pattern of electrons diffracted by a nickel single crystal. And they were able to show that their experimental data agreed with the diffraction pattern produced by a wave with the same wavelength as the electron's de Broglie wavelength. That same year, 1927, G.P. Thomson, son of J.J. Thomson, carried out a similar experiment on the diffraction of electrons. Thomson used a higher energy, a few kilo eV electrons, and gold foil instead of a single crystal. He observed a very similar diffraction pattern as that produced by X-rays, and this is an electron diffraction pattern of gold.